Welcome to the last Mathologer video of the year. Almost everybody who watches these videos knows that root 2, pi and e are irrational numbers. That these numbers cannot be written as ratios of integers. Also, a lot of you will be familiar with proofs of these facts in the case of root 2 and e. On the other hand, my guess is that very few of you will be able to say the same about everybody's favorite number pi. In fact, even many professional mathematicians have not seen a proof that pi is irrational, and are really just taking someone else's word for it in this respect. The main reason for this sorry state of affairs is that all the known proofs for the irrationality of pi are very technical and for the most part very unintuitive. My mission today is to make one of these proofs accessible to you by maxing out what can be achieved with the sort of animated algebra that I've been specializing in lately. The proof I have in mind was published in 1761 by the Swiss polymath Johann Lambert. And that was actually the very first proof of the irrationality of pi. Why Lambert's proof and not any of the others? Well, unlike all the other proofs, it is quite easy to motivate Lambert's approach, and the maths in it was really calling out to me to be animated. I just couldn't resist, okay? Anyway, let's get started. As a little warm-up, let me show you what is probably the simplest irrationality proof, a proof of the irrationality of log 3. If log 3 was actually a fraction u over v, that would be the same as saying that if I take 10 to the power of u divided by v, then I get 3. But then, raising both sides to the v's power, we get this equation here. But that is completely impossible because the left side is odd and the right side is even, right? And so, because our assumption that log 3 is rational leads to this false statement, and nothing false can logically follow from anything true, we conclude that our assumption has to be false itself. So log 3 is not a fraction, that means it is irrational. QED. Neat, huh? It's neat. Most of you like puzzles. So here are some one-glance puzzles for you. Which of these logs is irrational? Okay. Leave your answers in the comments. I'll grade them later. Just kidding. I really hate grading.
I like grading.
You are very strange. Marty is very strange. So hopefully that was all fun and really easy, but now on to the big challenge. Lambert's proof that pi is irrational. Here's a 3-step summary of the main ingredients. In step 1, Lambert proves a new miraculous formula for the circle function tangent. So tan of x is equal to x over 1 minus x squared over 3 minus x squared over 5 and so on, all the odd numbers in there, okay? In step 2, Lambert shows that if you plug in any rational number for x other than 0, you always get an irrational number. That's pretty amazing, isn't it? So tan of 1/2, of 3/4, all these numbers are irrational. But now the third and final step is really easy. You all know from school that tan of pi over 4, that's tan of 45 degrees, is equal to 1. But of course, the number 1 is not irrational. And this implies that pi over 4 cannot be written as a fraction u over v. In other words, pi over 4 is irrational. But if pi over 4 is irrational, then pi itself is 4 times an irrational number, which is also an irrational number. So pi is irrational. Now that's a really beautiful argument, isn't it? But as usual, the devil and the main bulk of the beauty of the proof is in the details. And of course, all the hardcore fans among you will ask for my head if I don't fill in those details, right? He's just laughing. Well, I'll do that in a moment, promise. But first let me put Lambert's proof and this formula in its historical context, which will give you an idea of how Lambert may actually have discovered his proof. Lambert was a contemporary of the mathematical superstar Leonhard Euler. In fact, when Lambert came up with his proof, Lambert and Euler were colleagues at the Prussian Academy of Sciences in Berlin. At that time, infinite nested fractions like the one discovered by Lambert were very much an in thing among mathematicians. These continued fractions, as they are usually called, were made popular by Euler, who had succeeded in proving all sorts of amazing results using them. For example, he showed that any number that can be written as an especially simple infinite fraction, in which all the numerators are equal to 1 and all the denominators are positive integers, any number like this is irrational. For example, this infinite fraction here with the simple periodic pattern of denominators 1, 2, 1, 2, 1, 2, 1, 2. Okay, well, must be irrational. In fact, this fraction turns out to be root 3, which is not too difficult to show and which you can attempt in the comments. Should I attempt it?
I think so.
I think so too. It's a nice one. And so Euler's result leads to a very pretty proof that root 3 is irrational. Even better, Euler employed the same irrationality of infinite fractions to give a first proof that the number e is irrational. And he did this by demonstrating that e can be written as this amazing infinite fraction here, with the numbers in the denominators continuing in the infinite regular pattern 2, 1, 1, 4, 1, 1, 6, 1, 1, 8, 1, 1, 10, 1, 1, and so on. Now, I already talked about all this stuff in another video, so check that one out too. And that's in order.
Jawohl!
Okay. Anyway, Lambert was undoubtedly aware of Euler's work when he came up with a great idea to turn 10 of x into an infinite fraction. He starts out with the basic fact that 10 of x is equal to sin x divided by cos x. Lambert then uses another well-known fact that the function sin x and cos x can be written as these pretty infinite sums. Now, I've already inflicted these sums upon you many, many times in other videos, so here I'll just run with them. Hope you're all okay with that.
What if they're not okay with it?
Well, let's just see what happens. Anyway, this means that 10 of x is equal to this beautiful monster here. Okay. Now we have to transform this monster ratio into Lambert's infinite fraction for 10x. In Lambert's manuscript, this transformation is an absolute nightmare. So, ready for the nightmare? Well, hopefully the animations, which only took me 10 million hours to create just for you, will make it all a lot easier to follow. In any case, now is a really, really good time to fasten your mathematical seatbelts, I promise. First, let's write all those powers of x as products like this. Very pretty, isn't it? Pull out a common factor in the numerators. Okay, now we're dealing with a product of x and a fraction. Okay, at this point I have to remind you of a little fraction trick that we'll be using over and over to build the infinite fraction. The product over there is the same as the quotient of x and the reciprocal of the fraction. Just think about it for a second. You're okay with that? Great. Now, the quotient at the bottom we can also write like this big nested fraction here. All good? Okay. Of course, this is simple junior school algebra, but we'll be using this trick over and over with the green and yellow expressions, both monster sums. So I thought I better make absolutely sure we're on the same page. Now let's unleash the reciprocal trick for the first time. Just watch it. Here we've got our project and abracadabra, it's real magic as far as I'm concerned. So we're off to a good start, great. Now if this 1 here was not there, we could move the common factor x squared out in front of the fraction at the bottom and repeat the reciprocal trick, right? But since the 1 is there, we'll first get rid of it using another fraction trick. I call it the add and subtract the same stuff from the numerator trick.
Catchy title.
Catchy title. Okay, so let's just launch into it. For the moment, don't worry too much about following every detail, okay? We add and subtract the green denominator to and from the yellow numerator. Whoa, looks scary, but really isn't.
Yes, it is.
Isn't. Just think about it. We've just added and subtracted the same thing to and from the numerator. That does not change the value of the numerator. Now, swap the top two sums and do some housekeeping. First, in the pink box, pull the minus into the brackets. Okay, now 1 minus 1 in the pink is 0. So we're about to get rid of the blue 1 as planned. Also for later, note that we get rid of the blue 1 using the other one here, which is the constant of the sum in the denominator, the green sum. Anyway, we just got rid of the 1 we wanted to get rid of. It's not clear how this will help, but just wait for it. Now some quick routine housekeeping on autopilot. Okay, that's minus 2/3. Pull it together. Okay, do it again and again and again. At this point we spot a pattern and can confidently say etc. Now the blue boxes contain the same stuff, and so the red fraction is equal to blue divided by blue plus pink divided by blue. But blue divided by blue is 1, and so we get 1 plus pink divided by blue. Now again, some easy housekeeping in the numerator. Pull out the minus, there we go. Pull out the common factor, there. Cancel common factors that I've highlighted here, and just generally clean up a bit. Very nice. Now we're ready to unleash the reciprocal trick for the second time. Just watch it, magic again. Magic, 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 yes. Now, rinse and repeat. Well, perhaps that was a little too much for you to handle in the next rinse on your own. So let's just go through the whole thing one more time, real quick. As before, we'll get rid of the constant in the numerator of the red fraction using the constant in the denominator. Now the blue is equal to 3 times the pink, and so this time we add and subtract 3 times the denominator to and from the numerator. Okay, now just follow our nose again. There we go. Okay, and this is the point where the numbers at the front get cancelled again. All right, now just some housekeeping again, and we're back to this picture here. Our red fraction at the bottom is now 3 times blue divided by blue plus pink divided by blue, but 3 times blue divided by blue is 3, and so we get 3 plus that. Clean up again, really quick this time. I promise quick. Okay, quick, quick, quick. Good. And we're ready for the reciprocal trick again. Okay, so let's watch it again. Magic, magic. And what's next? Well, we need to kill the 1/3 with the 1/3 times 5. And since 5 times the pink is equal to the blue, after the next reciprocal trick, we get the 5 out in front, and so on. Pretty neat, huh? There was 100 slides since I talked to fasten your seatbelts. Anyway, all these manipulations are definitely quite complicated, but in the end also very natural and something that a lot of you would have ended up doing if I had challenged you with the input-output of this manipulation. Especially those of you who know how to divide power series should have experienced an eerie feeling of déjà vu while you were watching me. Maybe one of you can explain the connection in the comments. Anyway, all this suggests to Lambert and to us that somehow this equality should hold. Well, we're not going to get anywhere with making sense of this formula unless I finally tell you how mathematicians actually assign a value to the infinite fraction. To motivate our rule for doing this, let's chop off the fraction at the first denominator. Okay, so we end up with a finite expression which evaluates to the function x. Let's graph both tan of x and x. Here we go. As you can see, the blue function x approximates the orange tan of x very well close to 0. Let's chop the infinite fraction at the second denominator and plot the new function. Amazing, right? The new partial fraction approximates tan spectacularly well. Let's keep going. Third partial fraction, fourth partial fraction, fifths, and so on. Overall, these partial fractions converge to tan x, and it is in this sense that tan x really appears to be equal to the infinite fraction. However, here's a little bit of bad news. Although Lambert's calculation starts with a valid formula for tan x and ends up with this infinite fraction, and despite what our graphing suggests, we cannot be absolutely sure that the equal sign between tan x and the infinite fraction is really justified. What's the problem? Well, let's just quickly switch back to the point where we said and so on. Here. You see, at any stage of the calculation there is one of these infinite monster fractions at the bottom. When we say etc., we simply discard these monsters and effectively hope for the best. Well, so what's really still needed at this point is a bulletproof proof that we really do have equality between 10x and the infinite fraction, in the sense that I just described. This part of the proof involves looking very carefully at all those chopped off partial fractions. Lambert actually does that. The calculations are again quite laborious, but in the end pretty much as straightforward as the ones that spit out the infinite fraction in the first place. I'll skip those calculations here, but I'll link to an article that has the full details. And if you ask me really nicely, I can also put a supplementary video on Mathologer too, where I nut out some more details. Anyway, for our purposes, I hereby declare Lambert's 10 formula under control. He's laughing again. Okay, hands up if you're still here.
Yeah, I'm here.
Okay, fantastic. You've all earned the Mathologer Algebra Merit Badge. But there's a little bit more work to be done and another real highlight to look forward to, an infinite descent into mathematical hell. Are you ready?
I can hardly wait.
Okay, so let's plug in a non-zero fraction u over v for x. And let's see how Lambert concludes that the tangent of this fraction is irrational. That then finishes the proof. Remember, the infinite fractions, like the one for root 3 or for e that I showed you earlier, were of a special simple type. All the numerators were 1 and all the denominators began with positive integers and pluses. And being of the special type, Euler had shown that these infinite fractions always represent irrational numbers. Lambert's infinite fractions are obviously not so simple. So Euler's result does not automatically apply to prove the irrationality of Lambert's fractions. This may seem like just a technicality, but in fact, there are infinite fractions that amount to rational numbers. For example, as a puzzle for you, you can try to show that the infinite fraction down there equals 1. As a harder puzzle, try to come up with infinitely many infinite fractions that are equal to 1. Anyway, to get somewhere with the irrationality proof, let's see how close we can massage Lambert's infinite fraction to Euler's special form. Getting rid of the fractions in the numerators is easy. We'll get rid of them one at a time. This animation of the transformation should be fairly self-explanatory. Okay, now let's show why, as long as both u and v are positive integers, the infinite fraction is always equal to an irrational number. That will then finish Lambert's proof. Now, apart from the very first numerator u, all the other numerators are equal to u squared. All right? On the other hand, the denominators get larger and larger. This means that from some point on, the denominators are all going to be a lot larger than the numerators. Now, there's a general theorem which says that any infinite fraction of this form is irrational. However, waving that magic wand now to finish off would be a bit unsatisfying, don't you think? Wouldn't be good, right? So let's see if we can convince ourselves of this directly. Just so that we can keep things within a small window, let's suppose that 5 times v, down there, is at least 2 larger than u squared. So from this point on, the denominators are all at least 2 larger than the numerators. Okay? All right. Now it's a bit fiddly, but with this extra +2 wiggle room in the denominators, it's now not too hard to show that just like u squared over 5v is a positive number less than 1, this whole infinite fraction here, which I've highlighted in blue, is also equal to a positive number that is smaller than 1. And the same is true for this infinite fraction here and for the following ones. What we'll show is that this positive and less than 1 property of all these nested infinite fractions implies that the first blue infinite fraction is an irrational number, which then implies that the number we are really interested in, namely this one here, is irrational too. Why? Because 3 times an integer minus an irrational number is irrational. A positive integer divided by an irrational number is irrational, and so on. Okay, so why is the blue infinite fraction irrational? Well, let's assume that it was actually equal to the fraction b over a. Remember, the infinite fraction is special in that it is positive and less than 1. But that means that b is less than a, right? Let's note this down somewhere. Now let's consider the size of the next infinite fraction. To do this, we just solve for it. Okay, here we go. Solve, solve, solve. Magic, magic, magic. And all the bits in the numerator are integers. And this means that the whole numerator is an integer. Let's call it c. But the yellow number was also special in that it is positive and less than 1. And that means that c is less than b. Let's also note that down. And now we repeat and solve for the next infinite fraction, which will generate a positive integer d less than c. There we go. And now repeating this infinitely often gives us an infinite sequence of ever decreasing positive integers. And now for the punchline. There is no such thing as an infinite sequence of ever decreasing positive integers. Why? Well, suppose a was 1000. Then we could count down for a while, but not forever. Eventually, we'd have to go below 0. And the same is true no matter how large an a we start with. We can only descend finitely many steps, each ending on positive integers, until we hit 0. And so, because our assumption that the blue infinite fraction is rational leads to this impossible infinite descent of positive integers, we conclude that our assumption has to be false itself. That is, the blue stuff cannot be a fraction and so must be irrational. What an absolutely beautiful argument to finish off things. Don't you think?
Lovely.
Lovely. Anyway, this was the last piece of our puzzle. So I hope you enjoyed my take on Lambert's beautiful proof. As usual, let me know in the comments what did and did not work for you. If you made it all the way to here, you earned yourself a special Mathologer seal of approval. Merry Christmas, fröhliche Weihnachten, and I'll see you in the new year.
Merry Christmas from Marty.